Let's talk a little bit about work. So we'll start with an example. And our example is going to be that a 600-pound boat sits on a ramp, inclined at 30 degrees. What force is required to keep the boat from sliding down the ramp? What force is required to keep the boat from sliding down the ramp? So let's see if we can draw a picture here. So here is our boat ramp, and this will be our boat. Whew, such artistic talent. This is a 30-degree angle down here. So we know, because the boat is 600 pounds, that it's got a force vector, its weight, that's going straight down because of gravity. And I'm going to call that maybe just B, the boat vector. And because it's going straight down, it's going to be 0 in the x direction and negative 600 in the y direction. So that's the weight vector for the boat. So what we want then is to figure out how much of that weight is, how much of that force, that weight of the boat is going in this direction down here. And then what we'll try to do to stop it is find, since we want the force, we want the magnitude of that vector that will counteract that. So this is going to be our force vector that will counteract the boat sliding down the ramp, and we're looking for its magnitude. That's what we're after here. So we can see that because of this 30-degree angle, we can see that this vector right here is going to be, I'm going to call that vector V, is going to be cosine 30 degrees in the x direction, sine 30 degrees in the y direction. So that's a unit vector in that direction. And we know that sine squared plus cosine squared is 1, so that's a vector of length 1. So what we want to get this, I'm going to make it green. So we want how much of this is going down there. So to find that, which is really going to answer our question of the magnitude of that force, is we want the magnitude of the projection of our boat vector onto that vector V. That's what we're really after here. That's will give us how much force we're going to need to keep that thing from sliding. And it'll have to be in the direction of this vector here. So we know how to do this. We can, it's going to be, in general, the projection vector is going to be B dotted with V over the magnitude of V. And so our boat vector, the weight of that thing, is that 0, negative 600. And our V vector is going to be right here. And I guess we can say, since we know the sine and cosine of 30, that this vector V, the cosine of 30 is going to be square root of 3 over 2, and the sine of 30 is going to be a half. So we're taking B dotted with V is going to be our 0 times the square root of 3 over 2 plus 1/2 times the negative 600. And the magnitude of V is going to be, since that's a unit vector, it's going to be 1, right? Sine squared 30 plus cosine squared 30 is going to be 1. And so that is going to be a negative 300. So that's the magnitude, and that's going to be measured in force. And the negative we don't really care about so much. It's probably going to counteract that, it's going to be a positive 300 pounds. And it's going to have to be in the direction here if we're going to keep that boat from sliding down into the water. Okay? Let's try another one here. Now we're going to talk here about work. So work is, we learned in our one-dimensional, we said that you may have gotten this in physics if you had it as mass times distance. So for us, the mass is going to be the magnitude of our force vector. So it's going to be the magnitude of our force vector times that distance. So if F, let's just say if F is a constant force, if F is a constant force whose direction is the same as that of vector AB, whose direction is the same as vector AB, then the work done by F, by our force F, in moving the object from A to B is going to be the magnitude of that force vector times the magnitude of AB, that distance. So that is, if you had some object there and you wanted to move it from point A to point B, you would just take whatever that magnitude of that force was, how much is it going to take to move that, times the distance. So that's our equivalent in a force vector of using the mass. So the magnitude of that force, how much is it going to take to move it, times the distance that we move it. Now what we're going to look at then is, well, what happens then if the force is not, so if our force vector here, we were saying, is going in that same direction from A to B. What if our force is not going in that same direction? What if it's, angled up over here somewhere? Then how do we figure out how much work is being done? So our idea is it's going to be a projection. So we want to know how much of that force is actually going in the direction that we need it to move that object from A to B. And so what that becomes is the work is going to be the projection, the magnitude, because we have magnitude of that force vector right here. So we can get the magnitude of the projection of our force vector onto AB times the magnitude of AB. That's how we get that distance, the distance from A to B. And let's see what we know about that. Well, we know how to find the projection, the magnitude of the projection of F onto AB. Remember, that's U dot V over magnitude V. So that's going to be F, the force vector, dotted with the vector AB that shows us how we're moving from A to B, over the magnitude of AB. So that much here. So this is exactly what that is. And then we're going to multiply that by the magnitude of AB. Well, how convenient that those cancel. And so what we get is something quite memorable and really, really nice to use. The work done is going to be equal to the dot product of the force vector with the direction vector. How far do we move that thing? That is how we're going to do work. Well, that's pretty nice and pretty convenient. So, see an example of that. So, our first example is going to be find the work done by a 10-pound force acting in the direction of the vector 1, 2 in moving an object 3 feet from 0, 0 to 3, 0. So maybe a picture here a little bit. So we're going to try to move this object, whatever it is, and we want to move it from 0, 0 to 3, 0. So we want to move it 3 feet this direction. Our vector is a 10-pound force, and it's in the direction 1, 2. So it's going to be something like this, and that's a 10-pound force. That's supposed to be a B. And so there's our force vector, and this is going to be our vector AB. So what we're going to do is we have to figure out how to write these vectors, but then we're going to say the work is going to be the force vector dotted with the direction vector. So our force vector, we have a magnitude of 10 times, and the direction it is 1, 2, but now we have to be careful there because that is not a vector of length 1. And so if we just multiply the 10 times the vector 1, 2, that's going to have a magnitude greater than 10. So we have to do what's called normalizing this. We need to make this vector here into a unit vector. So if I say, I'm going to call that just for the heck of it V, then the magnitude of V is going to be the square root of 1 plus 2 squared is the square root of 5. So a unit vector in the direction of V, I'm making up this notation, is going to be the 1, 2 divided by its magnitude, the square root of 5. So our force vector, so I need to put the magnitude of V under here. So that's going to give us a force vector that is going to be 10 over the square root of 5 times the 1, 2. So that's going to be a 10-pound vector times a unit vector in the direction of 1, 2. Well, we can rationalize that. Let's see, that's 10 square root of 5 over 5. So that's going to be 2 square root of 5. So that means our force vector is going to be 2 square root of 5 times 1, 2. Or if you like, 2 square root of 5, comma, 4 square root of 5. So there's our force vector. Our direction vector, AB, that's just going 3 to the right. So that's 3, comma, 0. And so the work done is going to be the force dotted with the AB. So we've done all the hard part. Now we're going to take that 2 square root of 5, comma, 4 square root of 5, and dot that with 3, 0. And so that looks like it's going to be 6 square root of 5. And if you throw that on your calculator, I think that's going to be, now this is work, so it's going to be a weird unit. So it's going to be about 13.416, and that's going to be foot-pounds is our unit for work there. Crazy, crazy. Okay, so now I'm going to, I'm going to change direction completely here, and I want to talk about what are known as direction cosines. So I'm going to call these direction cosines. So recall that in 2 dimensions, when we have this xy axis, if we had a vector that was, say, over here, then we would say its direction angle would be that angle that goes counterclockwise from the positive x-axis. Well, life is more complicated in 3D. So now we don't just have an xy axis, we have an xyz axis. And now our vector, if you can imagine this, let's see, we're going to come out this much and then come over and then go up, and that's going to take us to, here is our vector coming out in front there into the positive, positive, positive quadrant. Okay, so let's see, I'll say in 3D, so in 3 dimensions, we sometimes measure direction. We sometimes measure direction in terms of the angle, in terms of the angles between the non-zero vector, V, we're going to call this thing, and the 3 unit vectors. And the 3 unit vectors in the x, y, and z direction, we'll call those I, J, and K. The angles, alpha, beta, and gamma, are known as the direction angles of vector V. And the cosine of alpha, the cosine of beta, and the cosine of gamma are the direction cosines of V. So let's see what that picture looks like. See, I'm going to be challenged here. Let's see. So we have our green vector V there. So this is our vector V. Now our, how do I want to put, colors do I want to use here? So this now is our vector right here. Well, I is going to be, so I is that unit vector in the direction of the x-axis. So our angle alpha is going from the green vector V to the x-axis. That's the angle alpha. And the angle beta is going from the y-axis to that green vector there. And let's see, and then gamma is going to go from the green vector to the z-axis there. So there's your alpha, beta, and gamma. Okay, so if we're looking for the cosine of alpha, we know that comes from u dot v over magnitude u magnitude v, but that's going to be v dotted with the I vector. Remember, I is that unit vector in the direction of the x-axis over magnitude v times the magnitude of I. But if we say that v is going to be, we'll say its components are v1, v2, and v3, then when we take this dot product, the v1 is going to pick up the 1 in the I vector, but the others are 0. So that's going to give us just v1. Now I is a unit vector, so its magnitude is 1. So what we're getting is that the cosine of alpha is just v1 over the magnitude of v. And so then in a similar fashion, we can see that the cosine of beta, we're going to get, when we dot that with j, so the j, the unit vector in the direction of the y-axis is 0, 1, 0. So when we dot it with v, we're just going to get v2 over the magnitude of v. And in a similar fashion, we're going to get that gamma is going to be v3 over the magnitude of v. So what we see then is if we go back for a moment and look at that v, and we look at the unit vector in the direction of v, the unit vector in the direction of v, and this is sometimes called the normalized vector, the normalized vector when you make it into a unit vector, then that is going to be v over the magnitude of v, and so that's going to be v1 over its magnitude, comma v2 over its magnitude, comma v3 over its magnitude. So there's a unit vector in the direction of v, but we can see from what we did up above there that we could say that is exactly cosine alpha, cosine beta, and cosine gamma. That is our direction cosines. And so they're easy to find. You just take v and make it into a unit vector. You just normalize it. So those are the direction cosines. And because we know that's a unit vector, we also know that when you take its magnitude, its length, so cosine squared alpha plus cosine squared beta plus cosine squared gamma must equal 1, because that's a unit vector. Crazy, crazy. Okay, so let's do a quick example here. We'll say that v is going to be the vector 2i plus 3j plus 4k. So I'm going to give you this in ijk form. And can you, first of all, find the direction cosines? And then, what else do I want then? Find the direction angles, rather. Find the direction angles. So I want to know what is alpha, beta, and gamma. And then finally show that cosine squared alpha plus cosine squared beta plus cosine squared gamma really is actually equal to 1. So direction cosines, this actually isn't too bad. So we're going to find the magnitude of v, and so we're going to get 2 squared is 4, 3 squared is 9, 4 squared is 16, and then we'll take the square root of that. So that's 29, so square root of 29 is the magnitude. So if we now normalize v, so we look at vector v divided by its magnitude, so we create a unit vector in the direction of v, then that's going to be 2 over the square root of 29, 3 over the square root of 29, and 4 over the square root of 29. So there is our unit vector in the direction of v. And we know that cosine of alpha is going to be that 2 over square root of 29. And we know that the cosine of beta is going to be 3 over the square root of 29. And the cosine of gamma is 4 over the square root of 29. So we found the direction cosines, so that's part A that we did right there. Then to find the direction angles, we're going to just take those inverse cosines on our calculator, and you can do that. So alpha is going to be the inverse cosine of 2 over the square root of 29, and I think if you throw that on your calculator, I got 68.2 degrees. See if you agree. And in a similar fashion, taking the inverse cosine of 3 over square root of 29, I believe is 56.1 degrees. And taking the inverse cosine of 4 over square root of 29 is 42.0 degrees. So that's part B. That is the direction angles. And finally, part C, we can show that if we take, I'm going to show that cosine squared alpha plus sine, or cosine squared beta plus cosine squared gamma is 1. So cosine alpha is 2 over square root of 29. I'm going to square that. And 3 over the square root of 29 and square that. And 4 over the square root of 29 and square that. So that's going to become 4 over 29 plus 9 over 29 plus 16 over 29. So that is, again, 29 over 29, which is 1, which is what we wanted to show. Very good.